All right. So let's see. Put this back at the beginning. So if I want to draw an approximate accumulation, if I let one interval go by of 0.4 seconds at this relatively low rate, just kind of like we did with the plane, this is showing a weight of sand being slowly put onto the scale. Well, relatively quickly in reality, but over the first 0.4 seconds, since my rate that I'm using looks like about 75. I'm just making up an estimate visually from this. About 75 pounds per second, 3/4 of 100 pounds per second for the first 0.4 seconds. I could figure out where to put this dot, connect the dots, and do a graph. But I also know that for the next 0.4 seconds, I'm going to use a higher rate, and then a higher rate again after that. So between 0.4 and 1.2. So it begins to look, so I've got this low rate, here's my second piece, here's the third piece of function A, approximate accumulation of sand. If I go on from there, I know, well, the next segment comes from back down here, so I'm going to be accumulating sand still. The rate is decreasing, but it's still positive. So if I'm trying to imagine what this function A looks like, I've still got a positive rate, it's just not as positive as it used to be. But after this point, between 1.2 and 1.6, I'd have an accumulation of sand that seems to be, well, going up more and more slowly. And then for the last segment here that I can see, up through time 2, well, I'm just going to put it out to the end. There we go. This kind of levels off. So again, make sure whenever you're looking at graphs, you're realizing what they're a graph of. The one on the left here is our rate function. The one on the right is the amount function, or the accumulation function. So on the left, I've got how fast the sand's being poured onto the scale. And on the right, I have a graph that's showing the amount of sand in pounds that's on the scale. So using a constant rate for one segment at a time, I can get a relatively not pleasant to draw, but simple graph. It's just, in this case, I can see 5 or maybe 6 segments. Kind of hard to see when they're all very flat, it's kind of hard to see what's going on. Now, if I were to make delta x smaller, it should be a better estimate. Now, this one's a slider, so I can keep them up there. I'll just make delta x smaller and smaller and smaller and smaller. Let me stop at about 0.25. It's about 0.25. So if I have delta x instead of being 0.4 seconds, if I have it 0.25 seconds, there's a lot more separate constant rates that I'm going to have because I have a lot more intervals. If they're only 0.25 units wide, I'm going to have to measure the exact rate at more points in time. And I use each of them, though. So concept-wise, there's no new concepts involved. It's just more intervals of doing the same thing. But you see the graph on the right, it starts to look less chunky, less jagged, because the pieces are smaller, and the amount of change in the rate from one piece to the next would have to be less than it used to be, because we don't have a graph that goes up and down or anything crazy. So the rate from one section to the next, or the steepness visually here, is going to be able to be much more consistent from one piece to the next. And that's only changing from 0.4 to 0.25. If I go to like 0.1 or something, let's see if I can get 0.1. There's about 0.1 for delta x. Lots of segments, tedious to compute by hand. But that graph on the right looks pretty darn smooth, because just at the scale that we're at, it's hard to see the differences in the rates from one to the next. Now I can see in this graph that there are different rates. I have a rate around 0.7 and then a rate just like, so 75 pounds per second, maybe 110 pounds per second, 180 pounds per second, and so on. They are different rates, but when we only use each one for a tiny amount of time, visually speaking, it looks less jagged. And the smaller I get with these units, you can see the graph of A on the right isn't really changing anymore. And so what this is the effect of your estimate is close enough that it doesn't really make any difference. Now, depending on what you're doing with this, it could be very important that it's not as precise as it should be. But having 0.07 versus 0.005, those graphs of A look about the same to me. So why do I need to do more computations? Well, we weren't doing them by hand anyway. We can tell a computer to do whatever we want. But the idea is that there's this exact rate, this exact accumulation function A out there, and we're headed toward that. And the only step beyond what we've talked about so far is just, well, make delta x really small, which we're going to figure out what that means in terms of computations next week. But looking at our sum formation, all that does is change how many complete intervals there are, because delta x gets smaller. And where do we measure the rates? Because delta x ends more often. I'm going to have to evaluate the rate at more points, but I do the same process, just more repetition. So let's see, looking forward this guy. So thinking about our same diagram we had before, this red exact rate of change function, R sub f, and our approximate rate of change that we represent with these horizontal line segments. I can imagine this to be on any scale I want. Maybe these horizontal line segments are 0.00000003 units long. We're just zoomed in really close, whatever. There's numbers on this x-axis here from previous usage. But our idea is we're trying to figure out, if I know how fast something's changing at any point in time, I want to know how much of it I have, or how much of it I've generated or lost during any interval of time. So if I want to know how to accumulate between some general starting value of A, which doesn't have to be 0, we've used it as 0 most of the time, and when you're setting up a problem for yourself, you can redeclare the variables to, like, 0 means this, and so just kind of translate your whole function. But if we need to start at some point other than 0, this is the most general form that we can have, then we can do that. We just have to be careful about where we declare that each of our intervals is starting. So to measure this approximate accumulation, if we're writing it out longhand, like one accumulation during the first interval plus the second interval plus the third interval and so on, we'd have a whole bunch of terms that look like this. So the rate at the beginning, A, where we're starting accumulation, times the width of our interval delta x, whatever we choose for that parameter. So A and delta x are both parameters. They could be chosen differently and you'd get different results, but those are not extra variables. Those are just things that would need to be chosen to describe how you're doing the approximation. So this is the rate in the first interval times delta x, the width of the first interval, the rate that we use for the second interval, because we start at A plus one whole interval of delta x width past the beginning. So this is the rate at the beginning of the second interval times the width of that second interval, which is still delta x, the rate for the third interval times delta x, the width of the third interval, and so on, for however many intervals there are. And then just imagining if we do this a bunch, eventually we're going to get up to wherever our current value of x is, whatever that might be. Maybe it's a specific number like 17.4, or maybe we're just imagining some general x and we want to describe this. So if we want to talk about any current value of x, I wrote out a few terms just for the pattern there, but it could be that x is in the first interval. But all of these completed intervals, that's what forms the sum, the summation symbol portion of the accumulation that we have, where we have the rate evaluated at various points past A plus some whole number of delta x's, including 0 as a possibility. Each one of those rates times the width of the interval, if it's a full interval, a completed interval. And then we just have to express how many intervals there are. The small details will mop up in a second. But in the last interval, the x is in the middle of, if you want to think of it that way, the current interval, we want the rate at the beginning of that, which we called that the beginning of the current interval, we call left of x. And then the width of it depends on how far x is past left of x, which, just to describe this a little bit better then, just we're missing the top, the end of the sum. What's the last number that I'm going to use for my index value, for my j value here? And that's what we talk about. Oh, well, how many complete intervals are there? That's that, well, how far is x from a, and then divide by delta x, and take the floor of that. So I did have somebody ask a question about this the other day, but just if you're using a specific value of x, as opposed to just a general value like this, this is written assuming that x is something past a, x is to the right of a. You can also use it if x is to the left of a, but if you're trying to count how many intervals there are, you need to like take an absolute value if you don't just think about the subtraction. Because I just want to know how far x and a are apart. Typically we imagine x is larger than a, but it doesn't have to be. You just have to have the absolute value of that difference if you want to write it as a computation for any general x that could be left or right of a. But typically if we want to measure accumulation starting at, and there's a particular value, there's a reason that we have that as our starting value, because it doesn't make sense before that, or because this is some important point in the process where the rates are now definable, and prior to that they weren't. But the last detail we need is this, what's dx? If I describe that in terms of x, rather than having a second variable dx in this, that's just how far is x past the left end of the current interval, which is how big is x minus left of x. So this is our entire summation, or the entire description of how do I measure approximate accumulation. I need to have a starting point and an approximation delta x width that I've decided on, and that's kind of arbitrary, up to you. I also need to know the exact rate function and then pick out values of it every so often. So the way that this is written is with just plain r, but this could just be as well r sub f, or whatever the exact rate function is titled, because we're only evaluating it at the beginning of intervals, which means that r and r sub f are the same thing. R and R sub f, or R sub whatever it is, the exact and approximate rate functions have the same values at the beginning of each interval. That's how we defined our approximate rate function. So whether I say R of left of x, or R of x, or R sub f of left of x, those are all the same thing. This could be R sub f of all these a plus a whole number of delta x's, because again, that would form the left end of completed intervals, not the current interval. It was a previous left of x, but not the current one. So we could write this a variety of different ways. Yeah. So j doesn't have a meaning in terms of this. It tells us how to evaluate the sum. We're going to substitute in all the whole number of values from 1 through this in place of this j in that spot. So I'm going to start by substituting in 1 in this spot, and then 2, then 3, then 4, then 5, until I'm done with my completed intervals, until I've reached whatever this whole number is up there. So j is like a helper to help evaluate our function, to help us evaluate our function, our rate function in the right spots. So we're going to have an equivalent to that when we talk about exact rate of change, and it's just we have this second kind of temporary variable that's helping us figure out how to evaluate our rate function, or where to evaluate our rate function. And in this sense, we're evaluating our rate function at, well, if delta x is relatively large, you can imagine evaluating our exact rate function every so often. But if you imagine delta x is extremely small, it tells us to evaluate our rate function like almost everywhere, if you want to think of it that way. But j is a way to count how many intervals you've been working with. It's not the interval number, but we've made it match up with the interval number by writing this whole fancy j minus 1 thing. So j equals 3 would tell us about the third interval. And if you imagine substituting in j equals 3, I'd have r of a plus 2 delta x. That's the rate at the beginning of the third interval, which is 2 delta x units past the beginning, past A. But yeah, J isn't something that we see in any of these graphs. It's just something that helps us count the intervals or figure out where we're evaluating our rate function. So again, this is our approximate accumulation function. Although the smaller delta x is, the better approximation it is. And so we talked about this last time, but it's just putting together all of our principles from constant rate of change, which is why we focused on this for a while, because constant rate of change seems like, yeah, we did this a million years ago, but maybe didn't use it in quite this way, and it's really essential to the whole process of these approximations that we're doing. So the change in the dependent variable, dy, is a constant multiple of the change in the independent variable when we have constant rate of change. And if we imagine constant rate of change over small intervals, we can still use this principle for any defined rate function. So we've got this m dx sort of expression, the rate times delta x for the full intervals. And in the current interval that has varying length, we've got m times dx, a smaller amount, or dx is a length something between 0 and delta x. But it's the same sort of computation. It's a rate times a small amount of change in the independent variable to get the associated change in the dependent variable, using our differentials or our delta x here. And then the other part of constant rate of change, final value, y final, is y initial plus dy. So let me scooch this out of the way. But if I have a starting point, whether it's thinking about just an individual interval, or I can even think of adding up all of those. Like when we talk about how do I find a of 4? Well, I have to do all the accumulation from the full intervals. And then if I want to explain what's the equation for the third interval, for the third piece of a piecewise function, a of x, if I can put together, add up what all happened in the first several intervals, that's my starting point. And then I add on what's accumulating or what's happening still at the new rate during the current interval. So like with that a of 4 plus 3, I believe, no, it was 9, the rate in that third interval of the plane and the window problem, plus 9 times x minus 4. So all of these pieces apply when we're just talking about the dy equals mdx, and y final is y initial plus dy, dy also known as mdx. Those all apply when I've got one constant rate of change everywhere all the time, as well as if I have something that's smooth enough so that there's no corners where there's not an essentially constant rate. You did some questions where you zoomed in and found one of your functions had a weird cusp sort of point at a specific location, which if you have a sharp point, it doesn't matter how close you zoom in, it's not slowly blending from one value to another. It just suddenly changes from going down to going up or vice versa. Then you don't have an approximate constant rate of change near that point. But at any other sorts of points, in most applicable functions, things where you're trying to figure out what happens because of this rate, you don't have those, oh, all of a sudden this rate changes from negative to positive with not even a moment of constancy in between. So putting together all the pieces, then again, we do a sum over all the complete intervals, the first interval through the x minus a over delta x floor interval, however many that is. Evaluate the rate at the left end of each of those full intervals and multiply by delta x, the width of the interval. And then for our, wherever our x is, it's in the middle of some interval I can imagine. And if it isn't, this part just turns into 0 if it's at a boundary. But I evaluate the rate at the left end of the current interval, which is what left of x is about. Left of x is an x value. It's the x value at the left end of the current interval. R of left of x is the rate at the left end of the current interval. And then this current interval, haven't quite used it for delta x yet, otherwise it would have been a part of this sum. So it's going to be something less than delta x here, but x minus left of x, your current x value minus the x value at the left end of the interval will tell you how long you have used that current rate. So just to kind of sum up then, there are two fundamental problems that calculus addresses. And we talked about this the very first day. I think I had this exact same screen up. It says you know how much of a quantity you have, and you want to know how fast it's changing at every moment. Like we're looking at Usain Bolt running and zoomed in and tried to figure out how fast he was going in meters per second. Or the second one here, you know how fast a quantity is changing at every moment, and you want to know how much of it you have at every moment, which is what we've been working on with this whole accumulation sum. Starting from a rate function, how do I generate accumulation? How do I measure how much sand is on the scale? How do I measure how much oil has spilled? How do I measure how high this rocket-powered basketball is? Well, just using the rates, I can figure out net accumulation. If you give me some initial value, I can also tell you the total value, the total amount of sand, or the total value of the height, or whatever it might be. But these are the two halves. We're going to focus on, for the most of the, after this first test, we're going to focus on differential calculus for a while, but we've got a little bit of cleanup left to do. What's called integral calculus is what we've been working on for the past 3 weeks pretty consistently. After we talked about Usain Bolt, just talking about, so what if I knew what a rate graph was, or a rate function was, or a rate function rule was? How do I describe what happens due to that? And this is that whole summation we've got. So what we've done so far, if I have an exact rate of change function, R sub f, and I want to know how much I have, I'd like to get to an exact accumulation function. And we're almost there, but I know all the ingredients for it now. You know all the ingredients for it now. What we do is, you can imagine picking, relatively large intervals, delta x, so that you can physically see them, and then use each of these, a value every so often, every delta x, use that rate for a whole interval worth of width of delta x, because using those constant rates, and this blue graph, you could just also define that as R sub f of left of x, because it is just, each of those was the current value of the left end of the interval for a whole interval at some point in time. And then what we do is sum up all the changes due to those. So the change from the first interval using this rate, the change from the second interval using this rate, change during the third interval using this rate, and so on and so on. Whether they're big intervals like that, so we can see them, or smaller and smaller intervals, we find the amount of accumulation by adding up the change during each interval. And we end up with an approximate accumulation function. And this, by the way, this is that same graph of the sand that I just had up earlier. But the approximate and this mystery-like idea that there's some exact out there, well, I get closer and closer to this exact rate of change, or this exact accumulation function, if I make, instead of just realistically small delta x, if I make extremely small delta x's. And what we call this, when we make extremely small delta x's and let the size of delta x get closer and closer to 0, which we can't have it equal 0, that wouldn't make any sense. We could never have any change if we didn't change. We'd never pass any x values if we had a delta x of 0. But if we imagine it infinitesimally small, what that is called is using an integral. And that is next week's stuff, so I'll stop at this point. But just, if you see this phrase, integral calculus, that's what we're working to. We're just one step away from that. But I want to focus on the precursors to it, all the buildup. So we'll talk about details related to integrals next week after your test. So for today, though, we are done. Just as I said, remember to study. I'm not going to assign any additional homework. You have your homework number 8 that's due tonight. Look over the list of topics. Make sure you haven't forgotten things like, excuse me, hold on for just a minute. Make sure you haven't forgotten things like what it means for something to be a function, variables versus parameters versus constant, some of those kind of definition things we talked about. You will see a few questions, not too many, but a few on the test related to just those underlying definitions that we've used throughout. But constant rate of change and approximating accumulation, those are the main foci of the test. So read that list of things, and I will be in office hours tomorrow from 8 to 9, available on email other times, and there's plenty of other office hours spread around throughout me and the TAs. So study well, and I'll see you on Thursday, if not before.